Modern data engineering is hitting a hard wall. Data scale has grown at a rate that has outpaced the processing capabilities of any individual machine. Engineers relied on vertical scaling, adding more CPU power or RAM to a single server. But as data generation becomes exponential, the math for vertical scaling no longer works. To maintain performance, the system must be split apart. Engineers have to decouple storage from compute and spread the workload across a network of separate machines. This shift to distributed systems is the mandatory requirement for operating the modern web at scale. Success in these environments depends on a rigorous step-by-step architectural sequence, moving from basic distributed storage to complex real-time processing. Solving the big data problem is not a hardware fix. It is the challenge of orchestrating thousands of individual machines so they function as a single unit. This roadmap provides a structured path. Starting at the location pin, we identify foundational models. We establish conceptual foundations to ensure network logic is sound. Next, we move to storage platforms, managing massive raw data. Finally, we apply algorithms to extract insights. This progression is supported by industry-standard technical guides for Hadoop and Spark, which detail the specific configurations needed to meet these goals. This sequence builds from historical data storage toward the high-speed requirements of real-time analytics. The first layer of our architecture is the Apache Hadoop framework, which introduced the MapReduce model to the mainstream. Hadoop handled storage by splitting massive files into smaller, uniform data blocks and distributing them across a grid of server nodes. The logic of MapReduce is based on data locality. Instead of moving massive data sets across the network to the code, it sends tiny bits of processing code directly to the nodes where the data blocks live. In the map phase, each node works independently to filter and sort its local data chunk without needing to communicate with other nodes. Once mapping is complete, the reduced phase begins. The nodes shuffle their intermediate results and aggregate them into a single final output. If you were counting the frequency of a word across thousands of books, you would give one book to each of 1,000 people, have them count locally, and then sum their results. While MapReduce allows us to use cheap, commodity hardware to store massive amounts of data, it introduces a physical bottleneck that slows down the entire process. This bottleneck occurs at the hardware level. MapReduce is too slow for the needs of modern, dynamic data mining. The issue is disk I/O. MapReduce is designed to write its intermediate results back to physical hard heads after every single processing step to ensure data safety. For iterative algorithms, like those used in machine learning, the system spends the majority of its time reading and writing to the physical disk, rather than performing calculations. Physical read-write heads cannot move fast enough to support the requirements of instant interactive querying. To reach the final goals of our roadmap, the architecture must move processing away from physical disks and into the system's active memory. The Apache Spark framework was developed to solve this specific speed problem through high-speed analytics. Spark's primary upgrade is in-memory processing. It keeps data in RAM while it is being used, bypassing the slow mechanical read-write cycles of a hard drive. Spark SQL and its execution environment provide the technical logic for a more intelligent system. Before any code is actually run, Spark calculates the most efficient execution plan for the specific query. Rather than blindly executing code one step at a time, Spark analyzes the entire user query to see how the data will move through the cluster. It evaluates multiple pathways, eliminates redundant processing steps, and selects the most efficient route. This pre-computation step allows complex data mining algorithms to scale across thousands of machines without collapsing under the weight of the instructions. This transforms the distributed cluster from a simple storage repository into a high-speed execution engine. These architectural layers lead to the final objective, deploying a system capable of processing data pale-toys-on-took, or in real time. In this context, real-time means moving from processing historical batch data to processing live events the millisecond they are generated. Spark's intelligent execution plans and in-memory speed are the technical requirements that make real-time streaming possible. This creates a complete architecture. Hadoop provides the massive, reliable storage at the base, while Spark serves as the dynamic engine processing data in flight. This layered stack allows engineers to run complex data mining algorithms directly on live data feeds as they enter the system. This architecture enables the transition from analyzing historical records to providing millisecond-level responses to live events. This evolution began by breaking out of the single machine, moved into disk-bound MapReduce, and eventually reached the speed of Spark's optimized execution. Execution optimization is the technical layer that allows the modern data economy to scale. Mastering this architectural sequence is how engineers build the real-time systems that power today's digital infrastructure.